sort of share the screen, and as I said, let us sort of, yeah, it's here. Oh, sorry, yeah. So we seem to be in the practical class moving in faster in enzyme engineering than actually in the theoretical class. We have talked about enzyme kinetics and inhibition, etc., which really we will talk about much later in the class. So really, they are moving at different paces. Normally, the theory class moves ahead and the practical classes come later. We seem to have reversed the the order. But before I begin, any questions from the previous class? Because I don't want to now do any more of molecular biology. As I pointed out to you guys, that let us get back to enzyme kinetics. So if you have any questions, when do you want the quiz, etc., etc., all those things you can tell me in the next couple of minutes, and let us start the class. Or let us start the class and then we can discuss anything else that you want to discuss. As a matter of fact, I was not yet over with my background. I mean, I talked about the background in reaction engineering, which I thought is all familiar to you. I think there was nothing much to be added there. You're all comfortable with the reaction engineering part, so I don't really need to revise it. Is that all right? So shall we leave reaction engineering at the point where we stopped? And I would assume that you are familiar with the basic principles of reaction engineering, essentially batch, plug flow, CSTR, and the non-idealities associated with it, which allows you to make models and get residence time distributions that allows you to predict performance in a reaction. So while we will be focusing only on the fact, I mean, we will always be writing that ds by dt, the change of substrate reaction, is equal to Rx, I mean Rs actually, the reaction rate with as a function of substrate concentration. Really we are not, because this is actually by definition, because this is ds by dt reaction. And the material balance of how this ds by dt reaction becomes ds by dt accumulation is only true for batch reactors, and for CSTR and for PFR, etc. This is no longer valid because this material balance is not valid. So really we will focus only on this part. As far as enzyme kinetics is concerned, this part is something that you are expected to know. So actual performance in a CSTR, actual performance in a PFR, etc., is something which I am assuming that you are already aware of, and it is this part that we will focus on in most of the course. Is that all right? What are the various reaction rates that we are talking about? Essentially, that is the idea of this course. Where is this that we want to elaborate, because enzymes are complex catalysts, and that is how we look at it. I mean, we will not have time now anymore to talk about how enzymes function. That is a fascinating field, but we will just not have the time. Also, let me be honest, my understanding of biochemistry is rather poor, and how proteins fold, and how electrophilic attack and nucleophilic attack takes place, and how they capture the protein, and how they then how they capture the substrate, and how they convert the substrate by various electron donors and all that. Those beautiful mechanisms are there in literature, but it is something that I will not be able to cover or do justice to. I will mark this as some kind of self-study that I would like you to do, so as to understand the wonderful complexity of enzymes and how well and how proficiently they do this job. But we will not be doing it in a lot of detail. We will be doing this part. But even before I begin this part, one subject that I need to give as a background, but again, I sort of all the time I seem to be rushing without doing serious justice to any subject, is this whole notion of relaxation times. Are you familiar with relaxation time models and relaxation? Again, this is also revision. Relaxation time, yes, and their importance. You're familiar with this? I don't need to cover this as well. So essentially, so then I will quickly revise it in 10 minutes and then move ahead with kinetics. So very quickly, the essential idea is that in a CSTR, the model is V ds by dt. Accumulation is equal to F SF minus S, of course, minus the RS, the reaction rate. This could be ds by dt if it is a first order reaction. It could be whatever. I mean, RS into V actually. Let us be honest. Yeah. So it could be, for example, equal to, if I divide it by V, then we actually have ds by dt is equal to d SF minus S minus Ks if it is a first order reaction, right? In which case, of course, at steady state, the solutions were something which I pointed out to you, right? We just proved if at steady state, I just did we just get this is equal to this. So very clearly SF upon S is equal to K plus D upon D, right? We just showed that. And so now the real question is that suppose we have a CSTR and you are already familiar with the step input function and there is no reaction taking place. Then if we have some SF1, let us say, going to SF2, now the outlet with no reaction is actually SF1, which goes to SF2, right? And you're familiar with this basic CSTR model, which emerges from, this is your input function and your output function is something like this. You're familiar with this stuff, right? That's very basic, this is a first order system, as a matter of fact. Anywhere you are not familiar, we will do this very fast, but I don't want to waste too much time. But suppose there is also reaction taking place and the output of SF1 is S bar 1, given by this basic equation here. Right? So the S bar, this is the steady state function, so this is S. So for SF1, this will be S1, and for SF2, this will be S bar 2. So what is the rate of rise? How do we find this out? Can you tell me? So essentially you will write ds by dt is equal to dsf minus s. Now it is SF2 minus s minus ks, and of course s at time t is equal to 0, s here is equal to S1 bar. Are you with me till now? Because the steady state value of a reactor where there is reaction taking place at, say, first order, it could well be the Michaelis-Menten kinetics, but let us take first order for a simple case. Then this is the basic equation with this initial conditions, that S here is equal to this thing here, right? S1 bar at time t is equal to 0 is equal to d SF1, not SF2, upon K plus D. And this S at t is equal to infinity, this S will be equal to S2, which will be given by, of course, S2 is equal to d SF2 upon K plus D. Okay, is this all this stuff is familiar to you? Hello?
We can understand.
Sorry?
Sir,
like
I have forgot, but we can understand.
You've forgotten this, but you can understand. So anyway, then we will sort of, as I said, the whole idea would be to revise this very, very quickly and say, okay. And so really what we have is that, oh, why did I wipe out the whole thing? Oh, that's a mistake. So essentially ds by dt is equal to, what did I write? D SF2 minus S, I mean, I thought this I would sort of, minus Ks for a first order reaction, and with the essential boundary conditions, and we can then sort of solve this equation. How do we solve this? ये simple first order differential equation है, बहुत complicated नहीं है. तो मैं I think I was just sitting and solving it just now, so I will write it out for you. dk plus d, right? SF2 minus, and now this delta S. Delta S is really the step input, which really is, I'm putting it as SF2 minus SF1, just in case it is rising. And this rise will be e raised to of minus d plus k into t, right? Okay, is this solution make sense to all of you? The first steady state, the original steady state was, this is 2 actually. This is 2. Okay, so so when the input was SF1, and the output was then S1 given by the steady state concentrations, and then the input was raised to SF2 from SF1 का ये और SF2 हो गया. Now the output was, of course, it was lower than this. It was somewhere here, because obviously कुछ तो नीचे गिरेगा, and the output SF2 is here, but this change here will get into this kind of rise up here, and this rise up here will have a time constant given by this, rather than a time constant where the original equation was SF2 when there was no reaction, right? Was the E function was E minus dt. Remember delta S E raised to dt. I mean, again,
Yes.
I am sort of jumping. You remember this? So essentially what is happening is that the time constant of this system, 1 by tau, is actually 1 by tau 1 plus 1 by tau. ठीक है ना? Because अब आपका d, ये d है भाई, ये है 1 upon d plus k, है ना? This is 1 upon d plus k, so this becomes d plus k. This is 1 upon d, and this is, sorry, this tau, huh? समझ रहे ना आप? And this is 1 upon k. And so, if you can look at the relaxation time principles, essentially what we are saying is d plus k is equal to d plus k. ठीक है ना? तो 1 upon d plus 1 upon tau is d plus k is equal to 1 upon d plus 1 upon k. So we're essentially seeing that the relaxation times are getting added together. Sorry, the inverse of the relaxation times are getting added together. I mean, you can, I mean, if you want to, the far easier method is to not write it like this, because this become very tedious when you are doing multiple reactions, is to actually take the Laplace. Right? I mean, you essentially are writing this expression here, right? And you can write tau dx by dt plus x is equal to ft. This is essentially the form of the equation, isn't it? Ft is a step function. And you take the Laplace, you get tau s. Oh, sorry, again. Take a second, 1 second. Can you see the screen?
Yes,
Hello,
sir.
can you hear?
Yes, sir.
And
Yes,
then, so if you take the Laplace, you get essentially tau s, right? Sx plus x, that is all, x is equal to fs, where fs is the Laplacian transform of this, right? And so we essentially get x into tau s plus 1 is equal to f, right? And so x becomes equal to f upon, obviously, you get the point. Essentially, x becomes equal to 1 by tau s plus 1 plus f into f. That is the Laplace equation, and then we can solve it for. So we can solve most of these equations in terms of tau. So really, the argument that I'm trying to make is not actually solve your Laplace equations for you, but to say that the relaxation time, the time constants are important. And why are they important? Let me sort of not get into the maths at all. Let me sort of give you the concept, which is really important. The concept is that in biological reactions or in any such thing, and let me sort of give you an example so that it becomes more interesting rather than just a mathematical exercise, is that think about when you're working with let us say you're working with a CSTR, I mean, for all practical purposes. Now, there are there are reactions going on, there is cell growth going on, and the cell growth time constant is something close to mu, the rate of cell division, or some kind of kinetic constant K can be associated with this, and therefore a tau can be associated with cell growth. But let us also remember that these cells are also evolving in an evolutionary sense. There is, so let me sort of now reclear the canvas. In any reaction that you are studying, you have evolution happening of cells. You have actually the cellular reactions happening. And you have also, remember, quantum mechanical fluctuations. I mean, I'm just giving an example, sorry. I mean, I couldn't think of anything very clever. Some quantum mechanical fluctuations happening in the protein. I mean, proteins sort of undergo very fast, tiny quantum mechanical fluctuations, which are nowadays studied. Fluctuations in the protein. Fluctuations in the protein. And really what we are trying to say is that the time constant here are of the order of tensor of what? I don't know, 8, 9 seconds or something. मैं years को seconds में convert नहीं कर पा रहा हूँ. I'm so sorry, but मुझे मतलब maybe it's tensor of 8, but this is the tenfold error. So I'm really not.
Here is 10 to the power 7.
तो 100 साल तो नहीं लगेगा मतलब तो 7 ही लेना चाहिए ना. Tensor of 7. Thank you, Ratnesh. So tensor of seconds or so evolution is happening. एक साल में evolve कर जाता है. खटाखट देखिए वायरस और तेजी से कर रहा है, ओमिक्रॉन वगैरह, है ना. तो वो तो days में होता है या months में होता है. But then of course the viral count is also very large in the whole world population, so the probabilities are higher. But you know, of this order, and the reaction rates are of the order of 1 to 10 of 2 seconds. Fast reactions 100 seconds. 1 minute 2 minute में थोड़ा सा cell grow कर जाता है. Maybe at the most 10 of 3 seconds. And quantum mechanical fluctuations are of the order of, you know, if not nanoseconds, I mean femtoseconds, nanoseconds, whatever seconds. Now, the real question is, what are you interested in? These are the relaxation times associated with this. And you can saw that the relaxation times are additive when we study response of systems. So when our window of observation is in you know minutes, which means tensor of 2 seconds, tensor of 1 to 2, or not every second we don't observe. I'm just putting some crude numbers here just for comfort. If this is our window of observation, then really only things that will be changing is this. This is what we are observing. This is taking place very slowly. So this set of reactions, evolutionary reactions, are frozen in the initial condition. What do I mean by this? That because we are studying it for few minutes or few hours or few days, there is no change in the evolutionary pattern that you would observe. So yours for all practical purposes, the cells are not changing. They are not evolving at all. They are frozen in their initial conditions. Right? Assume that your window of observation was 1 year. Then obviously you would see cells evolving, and we do a lot of experiments in biology where we try to adapt the cell and grow the cells in E. coli or any other cell for that matter, and these cells evolve into different kinds of cells. People have grown cells for 1 year or more and found that the cell now has a different physiology, can take sugars up differently, and depending on the evolutionary pressure, develop antibiotic resistance, etc. But for all practical purposes, because you're doing reaction kinetics, you are not interested in the fact that these cells are slowly developing antibiotic resistance or they're adapting to grow on glucose, etc. They are assumed to be what they were in the beginning. So they are frozen in their initial condition. This is where the change is happening. So your window of observation will observe the changes that take place with the same time constant as your window of operation. Similarly, here these things have already reached equilibrium, as a matter of fact. If there was some minor fluctuation in protein structure, etc., Because it took place so quickly, for all practical purposes, we will treat this as some kind of steady state. This has already reached steady state because the time constants associated with this, the reaction is over. Whatever fluctuations, whatever changes are taking place, of course, I talk fluctuations, that was a bad example. Let us think of some protein going from protein structure A to protein structure B. This is taking place very, very fast the moment it folds. It happens in microseconds or nanoseconds. For all practical purposes, we will only see B or any steady state equilibrium concentration of A and B, if say they are in 50% ratios or whatever. So they reach equilibrium or steady state. So we see no changes because by the time we observe, it is this you are observing every 10 seconds or 1 second or 1 minute or 2 minutes or 1 hour. This has already the time constants associated with this are so fast that they have already happened. Am I getting through? This is an important concept. So there are people who do research where their time window of observation is in nanosecond fluorescence. So nanosecond fluorescence people are, for them, people studying nanosecond fluorescence, the protein is changing and that is the observation that you actually see. For them, the fact that the cell is growing while the protein is changing is unimportant. It is stuck in its initial condition. The cell biomass is exactly the same in nanoseconds. It does not change at all. It is frozen at 1 OD, it is frozen at 1 OD. It is not growing. It is frozen in its initial condition because my window of observation is in nanoseconds. So if this is the observation window, this and this are frozen in the initial conditions. If this is the observation window, if this is years of observation window, both cell biomass जितना भी grow करना है, grow करके steady state में चला गया है. It is in a steady state. And this has also reached a steady state or equilibrium depending on the situation, whether it's an open system or a closed system. Whether it's an open system or closed system, it is also reached steady state. And we are only looking at this. So if you're depending on your window of, and if this is your window of observation, this fellow on the left is frozen in initial condition and this fellow on the right has reached equilibrium or steady state, depending on the situation. Or dynamic equilibrium is a much easier answer because dynamic equilibrium represents steady state. Are you getting this argument?
Yes, sir. Like quantum mechanical fluctuations in biology, why do we need to why people study about that? Like biomolecules are big molecules, so for that.
इसका जवाब मैं नहीं दूंगा. I'm sorry, I will not reply to this. We have already deviated a lot from our basic. Some things, as I said, biology is a very vast field. Physicists, chemists, and biologists and engineers have got together to improve and change biology beyond recognition. And this is a fantastically growing field. I just cannot get into it, however much I may like it, because then I will losing my mandate of what I have to teach you. What I am, so why they study it? How nanosecond fluorimetry is used for studying quantum mechanical fluctuations, how molecular dynamics is used to study protein oscillations. These are things that I will not talk about. And what about the quantum mechanical formula that is used for understanding protein changes in proteins? These are things that I will not talk about. These are things that are out of the scope of this present course. These are interesting things that are done. I was using it only as an example for the fact that when your window of observation ensures that what are the changes that you will see where the tau values are close to each other. So your window, tau of observation window and the tau of the system that you are studying, tau of the system, if they're equal, that is where you see the change. If the window of observation is the time is far less than some other systemic change, this system change, this will be treated as a frozen in initial condition. And if your window of observation T observed is much larger than another T systemic changes, then this T system, this other system will be seen as having reached equilibrium or steady state. So it is only this section that you really need to model. That is the basic take-home message of this without the maths. And that is why I showed a very simple example of a CSTR where the K values and the D values were close, and therefore K plus D was the change of the step, was the response of the step function. Because so this is where you want to observe the system. All other components of the system which change either very slowly or very fast are treated as out of my model. This is the only part of the system that we model. But we forget that there are other things changing very slowly, which we don't model because we assume that they're frozen in initial condition, and other components which have changed very fast and hence have reached equilibrium or steady state already, so we don't bother about them. So we treat that this is already the condition and this is the condition. This is the essential take-home message of all relaxation time models. Let us say, for example, let us apply it for the very simple case of the kinetics that I will teach you. I will teach you kinetics, and all of my kinetics teaching will essentially assume that here is one protein molecule, and this is, say, the pocket where the substrate binds. And this is the substrate which binds. And whenever we talk of kinetics, we talk of substrate binding and some product leaving out of this. And this gets converted to some product. I mean, bad drawing, but doesn't matter. Okay, now this is, now there is some kind of, what do? We assume that this whole system is operating in some kind of steady state. It's coming, binding, coming. But when you add the substrate the first time, there is some small time involved in this steady state to be established. The product comes, binds, leaves, and then this steady state is arrived at. And that initial start time, when it reaches steady state, the initial start before it reaches steady state is of the order of microseconds. µs, microseconds. And so therefore, all enzyme kinetics velocities, which Arunangshu must have told you yesterday when he was talking of V naught, because there he was talking of the fact that product formation rate and T, this plot is like this, and therefore you have to be very cautious. And that is what he was telling Ratnesh, I think, who was saying, I want to put so much time, and before it take to so much time, then you know, because you are only in the spectrophotometer, you can only read P, therefore you will end to assume that this is the dP by dt. This is dP by dt, which is actually incorrect, because the real dP by dt is this, the tangent to the slope. This is the true dP by dt, which is V. This is V. And what you say, this is V, this is the mistake, because then you have to really do 10 minutes, 20 minutes, 30 minutes, 40 minutes, 50 minutes, and say, well, 20 minutes tak chalega, approximately. Theoretically, 2 minutes ke liye karna chahiye, 2 minutes ke liye aap kar nahi sakte experiment. So this is actually the V naught, right? And what you say is dP by dt by measuring P, and you call this as V naught, which is not necessarily true. As you can see, that the tangent to the slope will be equal to P by T only when this is a straight line. Remember this? Yes?
Yes, sir.
Yeah, but now let me sort of tell you the true picture, which is that P versus T plot actually goes like this. This part is very, very small. I have exaggerated it. This is in microseconds. This is in microseconds. This is the time that it takes for this steady state to reach. But because this is very small, for all practical purposes, we take this as a straight line here. This small time, if you study the moment you add the substrate, if you study that in the next microsecond, you will see no product is forming, because this steady state is being established. But because this time constant is very, very small, for all practical purposes, we assume that this equilibrium has been, or steady state has been reached. So we take it out of the model. You understand? So this is the whole idea of relaxation kinetics, where if you can find out the time constants associated with reactions and the time constant of time window of your observation, then you only study those with the similar time constants. All things with extremely fast time constants and extremely slow time constants can be safely ignored. And that is what makes relaxation time concepts a very powerful concept in simplifying modeling. Is this clear? I thought this is purely conceptual, so I just wanted to say it in a very, very conceptual way without the maths. As I said, I would have loved doing this maths, but it would involve a lot of Laplace, and I'm not very comfortable with it, and I also do not know whether I'll be able to do justice to it in such a short time period. But I think the concept can be said in words without getting into the maths, and I think the concept is important. Some of you might want to write a term paper on it. You are welcome. And look at relaxation time models and understand why they are so important and critical in biology, where the time constants from evolution to growth rates, to protein folding rates, to protein, quantum mechanical fluctuations, as I was. So these things have hugely varying time constants, right? So evolution is glacially slow, reactions are fast, and folding, etc., and many things are super fast. So depending on what is your observation will tell you what is the thing that you are studying, right? That is the essential, simple carry home message. Is this clear to all of you? So let us stop here and say that this is the second concept that I wanted to talk about. I will not go further ahead. I think it's good enough that you understand some basics of this. I mean, you said you're familiar with it, but I as from what I'm saying and your lack of response, I feel that maybe you are not. But yeah, let us begin. Let us begin the course finally. Yeah. So before I begin the course, as I keep on saying, this is my favorite line, I think. Let us first begin by the laws of mass action before we get into enzyme kinetics. Laws of mass action. I'm not going to talk about even simpler kinetics. That's all done in class 11. But let us revise laws of mass action. What is the law of mass action? A going to be the reaction rate V is equal to Ka. Right? These are the elementary reactions. These are called the elementary reactions. Elementary reactions. A going to be, so if it is 2A going to be, and if it is an elementary reaction, then V is equal to Ka square. Obviously, you understand that, right? So dA, for this kind of thing, dA by dt, we have equal to minus, dA by dt is equal to minus Ka, and which makes what A equal to what? If beginning is A0, then it has become A0 e raised to of minus Kt. Is the A value, right? Simple enough mass action kinetics with, of course, a K. So now really, and so the reaction rate, because A changes like that, dA by dt will be equal to K into A, which is this. So it will become K A0 e raised to of minus Kt. So this is how the reaction rate changes with time, right? And suppose you have, I mean, let us be very simple. Let us say that if you have, if it is indeed true that NA plus NBB B and so on and so forth plus NCC, and this is indeed the elementary reaction which is going to some product or set of products. Okay, products. क्या हो गया फिर से क्या? Can you hear me?
Yes, sir.
Yes, sir, we can.
Yeah. And then the velocity simply becomes equal to K, A raised to of NA, B raised to of NB, C raised to of NC, and so on and so forth. Right? Depending on, suppose it's 3, then we'll be taking 3 of these. You're familiar with this stuff, right? And if you have actually, so this is essential mass and action kinetics when these are the elements. If this is the elementary reaction, then if it is A, as I said, 2A, if it is 3A, then it will be AQ. It doesn't happen often, and it is very unlikely that this many molecules plus this many molecules plus this many molecules will. It is very unlikely that this would happen. It's very unlikely to have an expression like this. But just for sake of theory, that if this is the elementary reaction, this is what you will get, right? And essentially elementary models, the coefficient of the reactant actually goes to the power of the equation, right? Because of the basic concept of mass action kinetics, which is based on collision theory, right? So those many molecules have to come together. So yeah, that is the essential point. And of course, if the reaction is, say A plus B or whatever is going to C plus D, and of this is really irritating today. Is going to C plus D, and suppose this reaction is reversible. This is idiotic. This is really becoming idiotic. So if we are having A plus B going to, let me write it here, maybe that side if I write, then it's a problem. Then the forward reaction, right? The forward reaction is K forward, A, no power here, A into B. If there was some power, they would have put the power, and the reverse reaction is equal to K R C into D, right? Or if there was power here, some say N1, N2, N3, I mean suppose, and this was the elementary reaction, then we would put N1, N2 and N3, N4, right? And essentially, for the simplest case, if A going to be or whatever, we would have V forward is equal to simply K forward, or let me call it K1 A, and V reverse is equal to K2 B, right? This is the basic reaction kinetics. All of you are familiar with this?
Yes, sir. Yes.
Yeah, and so equilibrium is really attained when the concentrations don't change. So it really means Vf is equal to Vr. Correct? So therefore, by definition, K1A, for the simplest case, let us do it for the simplest case. You can do it for more complicated cases, or maybe I can ask it in the exam, is equal to K2B. Okay? And so if Vf is equal to Vr and Vf minus Vr is equal to 0, then if these are equal, then obviously K equilibrium, at equilibrium, K equilibrium is given by B by A. And what is B by A? What will be B by A? It will be K1 by K2. Or in other words, K forward by K reverse. Makes sense?
Yes, sir.
So obviously, I'm sort of quickly revising this, as I said, all this, a lot of revision, and obviously, therefore, in this case, C plus D or whatever, etc., typically, therefore, K equilibrium, maybe it's the red ink that I use. So K equilibrium is equal to, so C raised of N3, D raised of N4, and so on and so forth, divided by A raised of N1, B raised of N2, and so on and so forth, right? Which is also, notice, equal to K1 by K2, or K forward by K reverse. Is this all right? This is all class 11th stuff,
Yes,
but I sort of, yeah, so fine. I mean, रत्नेश के अलावा भी कुछ लोग हाँ बोले, या रत्नेश के हाँ बोलने से आप लोग चुप हो जाते हैं? मतलब ये क्या है? मतलब is there some kind of competitive inhibition or what? मतलब, you know, so what we normally talk about is an association constant. Association constant for, you know, Ka, for, let us say, usually because we do it with acids, I hope you remember that it is actually HA. Acids के लिए बहुत commonly use होता था, क्या था? H into A. याद है आप लोगों को? Class 11th stuff, है ना? So now what I will do is, I will also talk of a dissociation constant, which is also used for acids. Dissociation constant ये इक्विलिब्रियम से इमर्ज कर रहा है सीधा, है ना. I will also talk about dissociation constant, which will be given by Kd, which is the inverse of this. Okay, which is H into A upon HA. Right? So if we have HA, H plus A is your basic essential equilibrium. So what would be the ratios of the equilibrium to this? So if X is the amount of product formed, then what is K equilibrium? And you start with say 1 mole or 1 mole, and X is the amount of product formed, then what do we get? Am I right in saying, now let us see this. I mean, I want your opinion on this. X upon 1 minus X is equal to K equilibrium. Is this correct? Now, are you getting this? मतलब आप A to B कर रहे हैं, है ना? So now 1 minus A is, let us I mean I'm deliberately now sort of forget A to B, and at equilibrium X is the amount of product formed, so obviously the amount of product left, substrate left is 1 minus X. ठीक है? So X upon 1 minus X is K equilibrium. Okay, and therefore X is equal to what is it? X equal to what is the amount of product formed? K equilibrium. बताइए भाई, divided by, from this equation here, what do we get as X as? X is equal to, hello,
K equilibrium into 1 minus X.
अरे X का टर्म कैसे आएगा भाई? In terms of K equilibrium बताइए.
1 plus K equilibrium.
हाँ, thank you. That is why the thing has gone off again. 1 plus. Okay, so X can be determined from the equilibrium function. Okay. So now, before I quickly end the lecture, let me sort of introduce some concepts which are important, and I will not rub out everything. Let all this be there actually. As a matter of fact, ये rub out करना चाहिए था. So I will define two terms which make life a bit simpler, which you might have done earlier also, but just sort of. One I define is the mass action ratio. Have you heard of this mass action ratio? Seriously, God. Can all of you hear me still?
Yes, sir.
Hello?
Yes, sir.
Yes, sir.
लेकिन जो काम करना था वो तो किया नहीं इसने. All of you hear me? Yeah. Hello? Yeah.
Yes,
Can
sir.
all of you hear me? Yeah. So we define the mass action ratio gamma, right, as equal to actual amount. Let us take this equation here, for example. P actual in the system upon A in the system. Okay. So
Yes, sir.
is this clear to you? Okay. Now the mass action ratio is B in upon now gamma, and now remember that what is K equilibrium? That is given by the K equilibrium. So this is just the this is going to be, I'm going to throw this out. I'm in the other laptop. Now this is your mass action ratio, which is the actual B versus, and remember that at equilibrium X, what was the at equilibrium? This will be some B equilibrium upon A equilibrium. right? X can be found out, and 1 minus X can be found out. So at equilibrium, there is a certain concentration of B and A at equilibrium, and this is the mass action ratio. Okay, so I will now do one more thing, which is I will define the second term, which I will remove this association constants here. And I will define now using this gamma and the definition of K equilibrium. I will now define one more term, and these two terms then make life very easy, which is the rho. Sorry, rho, which I will call the disequilibrium ratio. Do you understand what I am doing? I am essentially looking at, and rho is defined as gamma upon K equilibrium. Okay? And do you understand what I am doing here? I am looking at a mass action ratio, which is the real value, and I am defining a disequilibrium ratio. Notice that if B and this, B in and B out, are equal to this and this, then gamma and K equilibrium are the same. So the disequilibrium ratio is 1. The disequilibrium ratio is 1. When it is equal to 1, then the disequilibrium ratio is 1, means the things are in equilibrium. And if it is far from 1, it is far away from equilibrium. Are you getting this?
Yes, sir.
Yes, sir.
Right. So we have the disequilibrium ratio is equal to gamma upon K equilibrium, which really is what? Which forget this for the minute. What is gamma? Gamma is B upon A, right? The actual values of is equal to B upon A, right? And K equilibrium, as we all know, is K1 by K2, right?
Yes, sir.
So what does this become equal to? This becomes equal to B K2. अब भाई आप लोग बताइए, ये बहुत मुश्किल काम नहीं है, upon A K1, which is this, which is also equal to what? The reverse reaction upon the forward reaction. So the disequilibrium ratio is nothing but the reverse reaction upon the forward reaction. So we defined a mass action ratio, which is the actual B upon actual A inside the cell or inside the reactor, and we defined an equilibrium ratio, which is given by B equilibrium by K equilibrium, which is equal to K1 by K2. We just know that simply. So the disequilibrium ratio becomes the ratio of the reverse reaction to the forward reaction. So essentially, what are we saying? We are saying that when rho is very much less than 1, then forward reaction is taking place. Forward reaction is happening when rho is less than 1. So when it is the disequilibrium ratio, when the disequilibrium ratio VR is less than VF, forward reaction is happening. So this is the normal situation. The values of B is small, the value of A is large, and so the disequilibrium ratio is less than 1, and so forward reaction is taking place. When rho is equal to 1, the system is in equilibrium. And of course, when rho is where is the space? When rho is greater than 1, then actually the reverse reaction dominates. It is actually not A going to B, but it is actually B going to A. Okay? Are all of you with me till now?
Yes, sir.
So we really are saying that the reverse reaction is, so we now have a very simple way to handle this stuff. How much time is left? Oh, we are running out of time. So we use these two very basic simple concepts of mass action ratio, which is gamma, and rho, which is the disequilibrium ratio, and we will work mostly with disassociation kinetics rather than association kinetics. And now can you tell me some very basic for example, okay, let me sort of jump here. What will be ln gamma? Sorry, not ln gamma, ln rho is equal to ln gamma. Wait, what is rho? What was rho equal to?
B in upon A in. Okay, no.
Haan,
Rho is equal
in terms
to
of
gamma upon K equilibrium.
gamma upon K equilibrium.
K equilibrium.
ठीक है, तो log ले लीजिए ln gamma minus ln K equilibrium.
Yeah.
ठीक है ना? और ये familiar लग रहा है आपको? What is this? What is this? What is this? RT से मल्टीप्लाई कर देते हैं कहिए तो RT ln rho कर देते हैं. ये तो मैं मतलब I'm just sort of लीजिए आपके लिए सिंप्लीफाई कर दिया. अब बताइए. So you remember delta G of reaction is equal to delta G naught plus RT ln K. याद है ना आपको इक्वेशन?
Yes, sir.
अब आपको ये और इसमें सिमिलरिटी दिख रही है ना आप लोगों को? है कि नहीं?
Yes, sir.
हाँ, तो now you see the advantages of this is why I was saying that these are the advantages. मैं यहाँ पे रोक रहा हूँ जानबूझ के. Let us, I mean, obviously I can stop here, or I mean, if you want me to, we can sort of simplify this and please remember these lines. I hope you understand. Remember these things, and then of course, as I said, for the simplest kinetics, I mean, let me go back and write it in terms of V is equal to now. As I said, for an A to B reaction, K1A minus K2B, right? ठीक है? Is equal to K1A common ले लीजिए 1 minus बताइए K2B upon K1A. I mean, so these definitions are very helpful. आप समझ रहे हैं? Okay? So it's equal to K1A 1 minus क्या है भाई? चलिए गामा अपॉन के इक्विलिब्रियम और वॉट एवर यू वांट टू पुट इट और इक्वल टू K1A 1 माइनस रो. ठीक है? Are you getting this argument?
Yes, sir.
So now instead of working with thermodynamic principles, you can now use the disequilibrium ratio and say essentially, and I can demonstrate it for larger issues, but I want you to demonstrate it. V is equal to V forward into 1 minus rho. ठीक है ना?
Yes, sir.
I will leave it to you as a small exercise, no marks, etc., no assignment, that you can demonstrate that this is true for this A N1, NA, B, NB going to C, NC plus D, NC. And this is the elementary reaction, and you write the forward reaction as K. Sorry. K forward into A raised to of N1 or NA whatever N1 B raised to of B raised to of N2, and then the V reverse is obviously written as K reverse into C NC D ND and so on and so forth. Whatever you do, you finally can derive this basic expression. So instead of doing reverse reactions and getting irritated, we can simply use the mass action ratio and hence the disequilibrium constant here and write your basic equation as simply V is equal to forward reaction into 1 minus this. Obviously, when this is less than 1, the forward reaction is fast. When rho is less than 1, it is very, very less than 1, it is V is equal to VF. When it is, as it is approaching 1, V is becoming equal to 0. And if rho becomes greater than 1, then actually V becomes negative, which actually means B is now forming A. So this is an easy way to handle reversible reactions, which is very important in enzyme kinetics. I'm sorry, I'm not going to cut it out. I'm going to stop here and ask questions. So these two very simple concepts in mass action kinetics allows you to incorporate both the mass action kinetics and the concept of equilibrium and hence reverse reactions. Is this clear? This is something which you must have known already. I'll sort of quickly revise this stuff. Are you okay with this?
Yes, sir.
Okay.
Yes, sir.
Thank you. So this was easy enough. Yeah, let me stop here, and next class we will handle some more basic concepts. Okay, thank you.
Sir, about the quiz, you mean?
हाँ बताइए.
Sir, can we have it on the 6th? On Sunday?
Today is 1st. 6th
Yes.
is
So,
6th
Sunday.
is what?
Sunday, sir.
Huh?
We can also have it on
Sunday?
Monday, 7th. Yes, sir.
Monday 7th.
Yes, sir. Yes, sir.
Monday 7th को आपका क्लास तो है नहीं?
सर नहीं क्लास नहीं सर, बट शाम में आई गेस हो सकता है.
Do you want to have the quiz in the first half an hour of the practicals?
Yeah,
And
yeah.
then do but your seniors are sitting there and waiting.
Sir, so we can have it, I think, in the, like, I don't think the practical would take more than 1 hour.
After the practicals or before the practicals, 1:30 to 2?
So I guess 1:30 to 2 would be better.
कुछ टाइम बताइए आप, मतलब you people have to, you are supposed to come up with a time and a date. You cannot fluctuate.
Okay, sir. We'll just discuss.
कल मुझे 100% tomorrow I want an answer. Okay, thank you.
Yes, sir. Yes, sir. But
100% time and date. Yeah.
Yes, sir. You can fix the date to 7th February though.
That's Monday.
Yes, so that's Monday. We can have the quiz on Monday. Yeah.
Okay, Monday. Monday there's a quiz on the topics, not what has been taught today. On the topics before today.
Okay, sir.
Okay, fine.
Thanks, sir.
Thank you.
Answer the quiz would be numerical based.
भाई मैंने अभी तक सवाल ही नहीं सेट किया है. अब मुझे बताओ कैसे सेट करें. How you give me an idea and then I can set those questions. How do I make a numerical out of transcriptomic rates and stuff like that? I'll try to make it numerical, but it is very hard to make a numerical question out of, and if I give you plasmid stability numerical, then it is almost impossible to solve because those are solutions of ordinary differential equations. And I hope you understand, right? I mean, as plasmids, free cells emerge and plasmid containing cells decline, I did not write the substrate balance, right? Deliberately, I did not write the substrate balance equation because the total amount of biomass has to remain the same. And then I did not write the yield coefficients. I mean, I deliberately avoided all those things because I wanted to teach the concept and not go into bioprocess. So in a CSTR, as the ratio of the cells change, the total cells remain constant because substrate is being utilized by both cells. So you cannot increase cells. I mean, you cannot have just, and cells cannot be increasing indefinitely. So one goes up, one goes down. That really involves solving a set of algebraic and differential equations. Now, I do not know how it can be simplified into a simple, doable problem in 15 minutes or whatever.
Yes, sir.
It is difficult. अब आप लोग मुझे मतलब इस तरह से ट्रैप करेंगे तो बड़ा मुश्किल होगा. मतलब I want to set a easy question paper.
Yes,
I
sir.
don't want to get.
Yes, sir. Please set up the question paper accordingly. I mean, we were just asking about it.
So let me think about it.
No, sir.
Sir, one more
in the
thing.
beginning, you said,
Sorry.
Sir,
One
I was
person
saying, yes, sir. So I was saying that we just talked and we said, sir, since it is a 2-hour lab, so let's, sir, can we keep the quiz from 4 to 4:30? Because even if the lab goes on for long, it won't take more than 4, and then all the seniors will also be not.
Okay, 4 to 4:30. Okay.
On Monday, sir. Yeah. Next Monday.
On Monday. All of you are agreed? Okay,
Yes, sir.
fine. Okay. Bye.
sure, sir. Thank you, sir.
Sir,
Thank you.
it should be better like if the quiz is before the lab. Like in that case, people will not concentrate
this is
on
what
lab.
I don't like. Ratnesh and please others. I mean, this is precisely what I find difficult. Please discuss it and tell me tomorrow.
Ratnesh isn't on the class WhatsApp group, so that's an issue, sir. Apart from the fact that 1 to 2 we have tutorials of other courses on Mondays. Most of us do. Yeah.
Okay.
Yes, sir.
Okay,
So
then
4 to 430 would be best because almost everyone else agrees, sir.
Okay.
Okay.
Thank you.
Thanks, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you. Thank you.
Thank you.
Thank you. क्या हो गया फिर जैम हो गया